Dear Father, we thank you for this day. Again, I thank you for this class. Just ask that you'd guide our steps today, help us to glorify you what we do, and just understand a little bit more about your creation together. Lord, in your name I pray, Lord Jesus. Amen. So I want to talk to you guys about the general concept of the derivative today. And we have had partial differentiation, right? And so we've looked at that, but we haven't really seen all these ideas together as sort of a coherent whole. So I just remind you to think back to Calculus 1, where we there had a story that we told about differential calculus, right? And that story was what? Given y equals to f of x, right? And, x equals to a, we construct y equals to f of a plus f prime of a times x minus a, right? This is the what? This is the tangent line, right? Now, you may or may not remember this. This is also known as the linearization of f at a of x, right? So that's the best affine approximation. If you like, you could also look at it like this. You could say, okay, so really, y minus f of a is equal to f prime of a times x minus a, right? So as a slogan, this suggests that the derivative at a describes the change at a, right? That's not what I want to say. It's the best linear approximation to the change at a is what I wanted to say. I'll find my words eventually here. The best linear approximation to change in y over change in x at a, right? I guess this, if I divide this over by x minus a, that's what we have, right? So it's change in y over change in x equals to that, right? So the derivative gives us the best approximation to the change in y over the change in x. But we can also look at it in terms of this linearization, right? The graph of the linearization is the tangent line. So now I want to talk about this same idea, but instead of just a function from, see here f is a function from r to r, right? This initial discussion here, we're talking about f is a function from r to r. So I'm just going to bump it up a notch, I suppose, just a little bit. So instead, if we look at a vector function that takes n variable input and outputs an m variable output, right? So here we'd have f is equal to it's got the first component function, the second component function, m of these. We have m component functions to f, all right? Then we can define the Jacobian of f at a point P as the following matrix. It's partial f, partial x1, partial f, partial x2, all the way out until partial f, partial xn. So this is and of course these, let me erase the p here. I just want to think of it at an arbitrary point for the moment, but this is an m by n matrix of partial derivatives. So m by n matrix. So you guys should be familiar with what a matrix is, right? That really should have been something you saw in high school algebra at some point. You might not know everything about it yet, but eventually you'll take Math 221 and you'll learn more, right? Or maybe you already have, I don't know, depends where you are. But this, we could write a couple different ways. We could write it like this, right? We could also write it as a stack of gradients. See, this is actually nabla F1 as a, as a row. Nabla F2 as a row. This T is for transpose. Nabla Fm as a row. The T is for transpose again. Technically speaking, my gradient vectors are column vectors, so I need a transpose to make them rows. Now, I could be more explicit here. The Jacobian matrix, it just looks like this, like partial F1, partial X1 is this one. Then I've got partial F1, partial X2 is this one, all the way on out to partial F1, partial Xn for the top row. And then this goes like this goes on. The bottom row would be partial Fm, partial X1, and then you've got partial Fm, partial X2, and so forth until you finally get the partial Fm, partial Xn. So it's an n by n matrix of partial derivatives, right? So this is the Jacobian matrix. This is actually the generalization of the slope for a function from R to R to a vector valued function from Rn to Rm. The Jacobian matrix plays the role that the slope previously did. Instead of one number, we need a matrix of functions, truth be told. And in this context, the linearization of this function, all right, at a point at x, the formula for it is something like this: f of p plus the Jacobian of f at the point p. Keep forgetting my vectors in here. Times x minus p. This right here is the best affine approximation to f of x near p. In other words, this is approximately equal to f of x, provided that we're close to the point of tangency. Right? Let me actually work one of these out just to make it a little bit less esoteric for you guys. So like example 1, let's look at f. I'm mapping from xy. We'll make it three-dimensional output. So let's do like x squared plus y squared for our first component, and maybe x for our second component, and then we'll do xy for the third component. Okay, so first of all, beware my notation. This is actually a column vector. If we write it in like explicit matrix notation, for me, this notation is a sneaky notation for column vector, truth be told, all right? So you guys help me out to start with here. What's the Jacobian? What's the Jacobian of f? You're telling me, are you telling me like components? All right, so what is that? Let's do the first column. First column's what? 2x, then what? 1. Very good. And then y. So that's the x derivatives of the function. The second column, y derivatives, we got what? We got 2y, 0. And what's the y derivative of xy? X. There you go. This is the Jacobian matrix of this function. So let's look at a specific point to understand like how we can use this to approximate the function of two variables. You guys pick the point. What do you want? Any point?
1, negative 3.
1, negative 3. I like that. So we'll look at the point 1, minus 3, right? So in that point, what's the Jacobian of f at that point? We plug in 1 for x, which gives me a 2. 1, and my y is minus 3, so I put minus 3 here. So that's a minus 6, 0, and 1. This matrix is the analog of the slope of this function at that point. And so the approximation, the linearization for this function at xy is equal to, oh, I guess I need to figure out what's f of the point? What's f of 1 minus 3? I also need to figure that out, right? I like the 10. And then what was the next? 1? Yeah. Negative 3? Yeah, that's right. So that's that. And so what we do is 10, 1 minus 3, plus my Jacobian matrix, which is 2 minus 6, 1, 0, minus 3, 1. And then I have to multiply by the change vector, like x minus p. What's x minus p here? X vector minus p is actually, for us, xy minus 1 minus 3. Sorry, this is violating my larger notational patterns, but it is what it is. So like this, in other words, like this x vector, not, the magnitude of this x vector is not x. So this is a violation of our usual notation, right? It might be better for me to go back here and instead of using the x vector to put like an r vector in its place if this is bothering you. If you don't know what I'm talking about, it's okay. Let's go on. So this is x minus 1. It's not a big deal. So y, hopefully you can understand what I'm about to write down. That, and now, so this is why this is not part of the required content of this course, because I don't really want to force you to learn how to multiply matrices. But if you could, what this gives you is, well, let me just leave it at that. Like this right here is the formula that this is approximately equal to, x squared plus y squared, x and xy, if we're close enough to the point 1 minus 3. That's the best linear approximation to that nonlinear function of 2 variables with a 3 variable output. Right? Now we don't, oh, that's actually not true. We do end up studying these kinds of things. What would this be? What kind of mapping would this be? We don't usually use x and y here, but like later in the course, we might talk about, we already talked about this a little bit, like uv maps to r of uv. What's this? Do you remember what this kind of mapping is? This is it could be a parameterization of a surface, right? So we could use this kind of calculus to like approximate a parameterization of a surface at a point. But that's what the general derivative is. The general derivative essentially is the idea that you can, if the function's differentiable at a point, this approximation is valid. All right? Now I make that more rigorous in the notes, but I don't really want to write that definition. I don't test on it in here. There's about 10 pages of the notes, just to be, full transparency here, guys. Basically from, page 180, I think. I'll just try to tell you specifically. So essentially from, section 4.4 on the general derivative is not something I test on rigorously in this class. All right, that's there for your edification and breadth of knowledge. This is the heart of it, though, is the idea that you can take a multivariate function and you can approximate it by the Jacobian matrix in this way. All right. So what does this have to do with what we've been doing? Well, it has much to do with everything we've been doing. Because if you look at specific cases of this, what's hidden in this one idea? Right? Let me use the projector here for a minute for that. I do want to spend most of today on tangent spaces, so I'm trying not to let this drag on too long. I do think it's important to talk about, though, because otherwise, like partial differentiation in isolation, it's not a coherent thought. Like the partial derivatives are really part of this Jacobian matrix. They're part of this general derivative. And if we understand it in the totality of that, it gives a deeper understanding. But I don't really hold your feet to the fire on this idea unless you take my advanced calculus class, which is where I do these things in more seriousness. But well, eventually it'll work. Yay. So here's, no one can read this, right? But let me make this like infinitely bigger. So this is that definition I was saying I won't write. That's this piece is actually just the Jacobian matrix times the, well, anyway, I'll try not to get into this, but here's the definition of the derivative in the abstract. It replaces the difference quotient. And anyway, getting to the point here is examples of this linearization idea. I already started. So first of all, if we do a plus h rather than x here, it makes it easier to look at. So like L of a plus h is f of a plus f prime of a times h. This is Calc 1, right? Now, we did this a little bit earlier in this class. R of a plus h is approximately R of a plus R prime of a times h. This is what? This is the tangent line. This is a parameterization of the tangent line where I've made it equal to 0. I've set the parameter to be 0. The parameter here is h at the point of tangency. But of course, the tangent line is the best approximation to the space curve at the point of tangency, right? Now, this is where we haven't talked about much yet, but if we have a function from Rn to R, then if I have f of r plus a, well, it's approximately the value of the function at the point, and it turns out that it's just the gradient of f times h, where I think I'm missing a dot product here, all right? The coordinate change map, we'll need this later, but if you have a mapping from, say, R3 to R3, this could be like x, y, z, or maybe the input is rho, phi, theta, and the output is x, y, z, right? That would be a coordinate change map. It's a mapping from R3 to R3 like that. And in that case, the Jacobian matrix is 3 by 3. We'll see this later in the course as we study change of variables for integration, because there will, you guys know how it goes. For u substitution, what do we have to do? We have to do what? We have to change the integrand and also do what? Change the du, dx and du, right? We have to change the measure. That's still true for multivariate integration. To properly understand that, we really need to have this idea in mind that we're trading a function of 3, we're making a 3 variable or a 2 variable change of notation. And it turns out that the way that the differential of area or the differential of volume changes, it corresponds to, as it turns out, the determinant of the Jacobian of the transformation. So we'll need this there. And then these are just some explicit examples. But that, more or less is all I have to say. If you read this section, I go into some great detail about ways that the directional derivatives can be deceiving. Basically, I point out in this section that, if I can find it, I point out that there's annoying things that can happen. Like, this is the standard example of a graph of a function which is not continuously differentiable. So here what you're looking at, the red, is a function that its derivative exists everywhere. In fact, the derivative at 0 is equal to 1/2, right? But that derivative function, even though it exists everywhere, it's not continuous everywhere, because in fact this function, the derivative, it ends up with, well, you can kind of see it from here. It's got like a cosine of 1 over x. And what happens to cosine of 1 over x as you approach 0? It just, like that, right? So the derivative is stupidly discontinuous at 0. And what that means is while the tangent line at 0 technically exists, it's a line with slope 1/2 that goes through 0, the tangent line doesn't really faithfully approximate the function there. See, because the function's not increasing at a rate of 1/2 close to 0. In fact, it's both increasing and decreasing if you zoom in on particular locales. So this phenomena of continuous differentiability, the lack thereof making things nefarious, continues in higher dimensions. But there's worse things for us in higher dimensions, like the directional derivatives can exist, and yet the general derivative does not exist. See, the general derivative, if you go back and you look at it, it was defined in terms of a multivariate limit, and the path limits are not enough to make that exist. So anyway, that is a summary of the 10 pages that you can kind of just gloss over, all right? So what I want to get to is the next thing I do test you on, which is the tangent plane. So basically, a lot of books just define a tangent plane. Oh, I'm sorry, guys. One other thing. If the other neat thing in section 4.4, before I forget, is you can see the chain rules just coming from matrix multiplication. Like if I take, G is f composed with x, where here G is like a function. Well, f is a function from R2 to R, and x is the what's this x? You guys tell me what this is. This is what? This is the polar coordinate change map, right? This is a mapping from R2 to R2. And the Jacobian matrix of this map is simply this 2x2 matrix. These derivatives should be familiar from last class, right? We did all these. And the matrix, the Jacobian matrix of the f is just this row vector, which is just the gradient of f put sideways. And if you multiply this row vector times that 2x2 matrix, like Math 221 tells you that this works out to that, you recognize these. These are exactly the r derivative of the composite and the theta derivative of the composite that we worked out yesterday. But you see, I'm deriving the rules from multiplying the Jacobian matrices of the maps which are composed. And all of the chain rules can be derived in this way, all right? Because ultimately the chain rule rests on the fact that when you compose linear maps, the composition of linear transformations is a linear transformation. So anyway, what I'm trying to tell you is the proof of the chain rule is above our pay grade because it requires linear algebra, and as such, I won't test you on it, all right? So those are the magic words you're looking for, right? But if you really want to understand it, come take my advanced calculus class. If you don't, stay away. But no, you should still come take advanced calculus because we do other things in there which are very, very fun, like variational calculus and some things that would make engineering make more sense to you. All right. So one other thing before I put this away, because I've got some cool pictures I want to show you. The problem we want to solve over the next story arc of the course, and this is a relatively short story, is how do we find the equation for the tangent space, right? How do we find the equation for the tangent space to a surface? So that kind of goes hand in hand with the question of how do you find a vector field which is normal to the surface everywhere, like a so-called normal vector field. So as we think about surfaces in 3 dimensions, there's really 3 ways we can go, right? We either talk about a level surface, f of x, y is equal to 0, or we can talk about a parametrized surface, something like, a mapping from R2 to R3, or we can think of it as a graph, z equals to xy, right? This is kind of a halfway house between these 2 viewpoints. And so in all 3 of these cases, we'd like to learn how can we write the equation of the tangent plane, and how can we find the normal vector field? Now here's some normal vector fields. The normal vector field picks out a side to the surface, you see? So if you look on here, there's these little black arrows. Those are the normal vector fields. Like here's a plane. Apparently this side's up, right? This wrinkly blanket thing, this side's up. As you can see, there's your little normal vector field, all right? And the white, the grayish lines, those would be like lines of constant parameter if we thought about it as a parametric surface, right? Down here is a donut, or some people call it a torus. And as you can see, I've given it the outward pointing vector field. As a point of order, if we want to orient the surface in the positive sense, we like to make the normal vector field point out of the surface if it's a closed surface. This is not a closed surface, that's not a closed surface, this is not a closed surface, this is a closed surface. What's the difference between a surface which is closed and one which is not? And when I say that these surfaces are not closed, I mean that in the understanding that these graphs are just a microcosm of a much larger global picture which goes on and on without end. What's the difference between this closed surface and these guys? Can you guys tell me? It doesn't go on and on. Yeah, that's true.
Does it come back around to itself?
It comes back around to itself? It does that, that's right. The closed surface, yep.
It has a set surface area?
Has a set surface area. That's also true, good, yeah. How about this? What's the difference between an open fence and a closed fence? Like, if I have, a fence around me and it's not closed, right? Versus if I have a fence around me that comes back where it starts. What's the difference between those two fences?
You can walk through the one.
I can walk through the one, right? How about this? One has a what? One has an inside and an outside. The other one does not, right? There's no inside and outside if the fence doesn't really have a close, if you think about it. Did ever guys tell you guys the joke about the mathematician, physicist, and the engineer?
Maybe, but I'd love to hear
Should I tell you again? Yeah, I don't think I've said it in here. So, a mathematician, an engineer, and a physicist are given a fixed length of fence, and they're asked to enclose the maximum area. So, first of all, the engineer says, "I'll make it square. It's got great economy. It can be replicated. It's just a good design, a solid design, a square. I'll make a square fence." All right. The physicist says, "Oh, well, I'll make it a circle. That has perfect symmetry. It's beautiful, right?" The mathematician, he takes the fence and he puts it any old which way around him, and then he says, "I'm on the outside."
Yeah, I don't get it.
Well, if this is the Earth, and this is my fence, and I'm out here, then this is in.
Oh, wait, that's genius.
That's right.
Yeah, I got it.
Yeah. So, I've told this joke in various different classes. I've told this joke in college algebra before, and got zero interaction, like no laughs, complete and total bombing. It was amazing. That wasn't my anyway. So, all right, guys. So if you look ahead to your next mission, I know you're already doing that because now that you've finished the previous mission, your life will not be complete until you have more of my homework to do. I understand that. Although I would point out, if you're not taking my class, I do post homework online, so you can always do my homework even if you're not in my class, just for fun. It is a service I provide. But joking aside, you should start working on the next homework soonish, right? Like as soon as you have the concepts needed to work the problems, then that would be a good time to start chipping away on that homework, right? So that it doesn't, creep up on you. The other thing I should mention, as it was reminded to me this morning, is that I have solutions posted online to some of your problems. So it may be that one of the problems in the homework is actually just straight up solved in my end of chapter problems. I was reminded, for example, that the insect ninja problem is actually solved in the end of chapter problems. I'd forgotten about that. Sorry. Because I talked to you about that. Did I remember that? No, if I'd known that, I would have told you, right? I did not, though. So the good news is we found about the same answer. I don't know. So tangent space. Or let's say not tangent space. My bad. Normal vector field. And tangent space. Number one, if we have f of x, y, z equals to a constant, defines, a surface S, then the normal vector at such a point, x, y, z, is given by what? We just use the gradient of f. Example. So if I have f of x comma y comma z equal to x squared plus y squared plus z squared, and let's suppose that it's equal to r squared because, well, that's an interesting example, right? That's the sphere of radius r centered at the origin. Then the normal vector field to that, one of the ones we could use, would just be like 2x, 2y, 2z. Now, that's not a unit normal, right? But suppose you want to find the equation, for instance, how to find equation of tangent space. Can you guys tell me? Well, I say tangent space. I meant to say tangent plane here. And let's make it more specific. X squared plus y squared plus z squared equals to 25. And what's a point on there? How about 3 minus 4, 0? Is that a point on that sphere? I think it is. So the normal at that point is what? It's 6 minus 8, 0. And then that's a normal. This gives a normal to the tangent plane. So what's the equation of the tangent plane? I guess this was example 2. Seems like that other thing I did was an example. But it's what? It's 6 times something minus 8 times something else plus 0 times something else equal to 0. X minus 3, y plus 4, and z minus 0. In other words, we got 6x minus 8y equal to what? 18 plus 32, 50. So there you go. That, my friends, is the equation to the tangent plane to the sphere of radius 5 at the point 3 minus 4, 0. You guys can do this, right? You can find the equation to a tangent plane. You can find the equation for the tangent plane to a given level surface at a point. It's not bad, is it? I don't think it's bad. What if we had a parametrized surface? How does this go in that case? It's a little bit trickier there. If we have, let's say, R of a mapping from some subset of R2 to R3 defines R of D equals to S, a surface, where we'll use, R. You got your choice. I usually use U and V. Let me use U and V. It's a kind of standard notation. It's a little bit obnoxious because U and V look too much alike, but I try to make my V's super jagged. So there's my best attempt at it. Okay. But of course we've got X of UV, Y of UV, Z of UV. These are my component functions to the parameterization. If I picture the surface, right? What happens if we freeze out, let's let P equal to a I usually have P naught be R of U naught V naught, okay? So there's a particular point right here, that point P naught, right? And so if you think about it, I can run two different kind of curves through there, right? I can run this kind of curve, where a typical point on here is given by, you know, let's say, I need a name, let me call it alpha. Alpha of U is equal to R of U comma V naught. So my alpha curve at the moment, for lack of a better notation, what is it doing? It's freezing V equal to V naught. So it's basically, you know, this is a line of, this blue line here, you could describe it by V equals to V naught, right? We're freezing the V. And we could also look at another one that goes through that point like this, right? We could make this the line where U is equal to U naught. And the formula for this guy maybe would be beta of V is R of, well, U naught comma V. I'm trying to make my V's jagged here. So check this out. Alpha prime, these are vectors, right? Alpha prime of U naught is equal to something. Beta prime of V naught is equal to something else. What are those? Think about it. We're differentiating, if you look at it, we're differentiating R holding V naught fixed, right? That's exactly partial R, partial U at the point, and this is partial R, partial V at the point. In other words, the partial derivatives of this map with respect to the parameters U and V, they define velocity vectors along the coordinate curves. I call these partial velocities. They're partial velocities of the parameterization. The partial velocities of the parameterization lie tangent to the surface. So how would I find the normal vector field in this world? Like, let me just, you know, I've got like this vector, right? And I got like that vector. This is my partial R, partial U, and this guy is partial R, partial V, right?
Cross product.
I hear cross product. Yes, indeed, that is the evil we must do. I guess, can you guys see if I write down here? So the normal vector at UV is partial R, partial U cross partial R, partial V. That is how to find the normal vector. This actually defines normal vector field. Because the discussion I've just gone through at the point P naught can be replicated at any point on the surface, provided that the parameterization is regular. Right? So to say that the parameterization is regular is to say that the partial velocities are not collinear. In other words, that the partial velocities have a non-vanishing cross product. If this cross product of the partial velocities is zero, that speaks to a degeneracy of the mapping, a degeneracy of the parameterization. It's not really a good parameterization of a surface if that happens. If partial R, partial U is zero, that means that the surface drops dimension. It's not really a two-dimensional surface, it's something else. It's like a point or a one-dimensional thing or something worse. Like a cone. If you tried to parameterize a cone, you'd find that you couldn't find the tangent space at the point of the cone. All right, so let's work an example with this idea. As you can see, which is easier, to find the normal vector field for a level surface or for a parameterized surface? Level, quite clearly level is much, much easier. So example 3, I'll try to take it easy on us. So suppose R of UV is like U squared plus V, UV. Let me just make that a U and I'll make this a U cubed, all right? if we do this, partial r, partial u is what? 2u? 1. All right, great. And partial r, partial v is 1. It's x hat, right? So if we want to calculate the normal vector field to this one, it ain't too bad, right? We've got to calculate, partial r, partial u cross partial r, partial v. That's, by the way, this is right here. This is the definition of the normal vector that's generated by a parameterization. We insist on doing the u derivative first, cross the v derivative second. That defines which way is up. You notice that if I switched the v and the u, it would turn that vector over upside down? So the choice of u then v matters. Anyway, so here we've got, 2u x hat plus y hat plus 3u squared z hat, and I'm taking the cross product with just x hat. So that gives me minus z hat plus 3u squared y hat, or if you like in the other notation, 0, 3u squared minus 1. I hope you found that using your usual formula. That's the normal vector field. So if I want to find the equation to the tangent plane at a point, I need a point. What point do you guys want?
1, 2.
1, 2? So r of 1, 2 is what? One squared plus 2. Oh yeah, 3. 1, 3, 1, 1. Okay, so this is a point. N of 1, 2 is what? 0, 3, minus 1. Put these together. My equation for tangent plane is what? Zero times x minus 3 plus 3 times y minus 1 minus 1 times z minus 1 equals to 0, or if you like, 3y minus z equals to, what we got? 2. There you go. This, my friends, is the equation for the tangent plane to this parameterized surface at the point which you guys picked. Right? So this is how we find the equation for the tangent plane and also the normal field for a parameterized surface. What's the third case to consider? The third case to consider, right, is, what's that? R2 to R2. No, we're still talking about a surface. We're talking about a surface in R3, but the other competing viewpoint is graph. So we'd have z equals to f of x comma y, right? And so suppose you want to find equation for tangent plane at, let's say, the point x naught, y naught, f of x naught, y naught, right? That would be a point on the graph. What do you think? How would you suggest we do it? We could either look at this as a parameterized surface with parameters x and y. If we did that, right, to make contact with the equation we want here, we would do what? We would need, we need to take the cross product. I don't like that. How can you reformulate a graph as a level surface? What do you do? How about this? We just do f of x comma y minus z. But if we want the if we want the normal to be pointing upward, if we consider positive z to be upward, this would be the wrong choice. Because when I calculate the gradient of that, I get a -1 in the z component. So maybe, despite the fact that it's a little bit more awkward, we should instead do z minus f of xy, right? If I do that, then the gradient of f is just straight up minus fx minus fy 1. And so the gradient of f at the point that we're interested in is, minus fx at x naught y naught, fy at x naught y naught 1. And so we have the equation minus f sub x of x naught y naught times x minus x naught minus f sub y at x naught y naught times y minus y naught plus z minus z naught equals to 0, which you can solve, and here's the takeaway message. This was z naught. For f of x naught y naught plus f sub x of x naught y naught times x minus x naught plus f sub y of x naught y naught times y minus y naught. And that right there is the equation of the tangent plane to a graph at the point. And that is the most direct analog to what I started this lecture with about the tangent line. This is the tangent plane to a function of two variables. Instead of one slope, we need two derivatives like this. But there you go. That's the equation of the tangent plane. So for a graph, we can do this, right? So we do all three of these things, and we'll talk more about them in a future class, but I think that's it for today, guys. Have a good weekend.